Hello everyone, this is Shady Elkassas, Head of Science Department, Charge American International School, and today we are going to revise the Electromagnetism course for grade 10. I have some specific objectives. Basically, any physics exam is classified into two main parts. So you have the problem solving and you have the theoretical part. So the main target today is to revise the theoretical part because it will cover most of the definitions and the ideas discussed in the course. So let's first of all introduce to the problem solving objectives that we will cover in a later video. Basically, you need to be able to calculate the electric force using Coulombs law. The second objective is to calculate the electric field strength, which is E, using the two formulas that we will discuss later. Also, you need to be able to calculate the electric potential energy and electric potential difference. Those are two related concepts. Because one of them is an electric potential energy and the other one electric potential difference, you need to be able to differentiate between both or between the two values. Then you need to be able to calculate the capacitance and then the electric power, and then to calculate the voltage, current, resistance using Ohm's law. Finally, you need to be able to calculate the power. So these are the values that you need to be able to calculate in the problem solving part. But today we are going to focus on the theoretical part, and the theoretical part includes many questions such as fill in the blanks or multiple choices questions. So you need to be able to define most of these physical quantities, and also to be able to discuss and explain some ideas related to the theoretical part. So our objectives for today would be define each physical quantity calculated here in the problem solving, such as the electric force, electric potential energy, electric potential energy, and then electric potential difference, capacitance, power, current, resistance, and power. You need to be able, here we repeated power, so you need to be able to calculate all of these, to define all of these values. Then you need to be able to compare the units and to derive them. So comparing the units and deriving them would be very important. Also, we need to be able to state and explain the properties of a charge and to mention what's the meaning of the conservation law of a charge. We need to be able to compare between the insulators and conductors. Also, we will be comparing between the different methods of separating charge, like conduction, induction, and polarization. We will recognize the direction of electric field lines, especially if you have same or different electric charge. We will recognize the direction of electric force between charges. We will recognize the structure of the electric circuit. And we will compare the series and parallel circuits and how we can calculate the equivalent resistance for both. And finally, we are going to define the role of the voltmeter and ammeter in a circuit. So first of all, we need to compare or to define the meaning of an electric charge and the interaction of, or the properties of the electric charge. So as you can see that one of the most important properties of charge is that the like charge repel and the opposite charges attract. So if you have a positive and positive, it repels and they repel, and if you have negative and negative, they repel. But if you have a positive and a negative, so they attract. Also, there is another important property, and we say that electric charges are quantized, and we mean by quantized means that they are conserved. So what do we mean by that is electric charges are conserved, and this is related to the conservation law of a charge. So for example, if you are rubbing a comb against your hair or a plastic ruler against your hair, if you have taken 5 negative charges on the ruler, this means that there are 5 positive charges on your head. So this is the meaning of quantized or conserved. The number of given charge should be equal to the number of the left charges. Here, as you can see, when we rub a glass rod with a silk cloth, as you can see, the glass rod is taking a positive charge, and the silk cloth has a negative charge. If you counted the number of charges, you'll find out that 1, 2, 3, 4, and 5. Then count the negative charge, it will be 1, 2, 3, 4, and 5, which means that electric charges are quantized. So this is the second property of a charge. So the first properties of a charge is that the like charge repel and the unlike charge attract. The second one is that the electric charges are conserved or quantized, which means that the amount of taken charges are equal to the amount of the left charge on the surfaces. Another important point here is that the objects basically differ in the type of a charge that they take. So take for instance a rod of glass when this rod is rubbed with a silk piece of cloth, it gets a positive charge, while a plastic rod gets when it's rubbed with fur, so it gets negative charge. So it depends on the type of the object and the type of the cloth itself, whether it's taking negative charge or leaving negative charge. So the glass should be positive and the plastic should be negative. Here we need to identify the methods of charge, and methods of charge we discussed them in the class, and they are basically it could be conduction, which is a direct contact. So if you have a positively charged object, when you have direct contact with the electroscope, this is basically an electroscope, this is a metal sphere that has an indicator. So with the direct contact, this is what we call conduction, and the conduction means that you transferred the same type of electric charge to the object. So as you can see, this is a positively charged object, and at the end also the electroscope became positively charged because there is a contact between the two objects. So conduction means a direct contact between a charged object and another one. The second way of charge is induction, and induction is an indirect charge or charging with no contact, with no direct contact, and it takes place only for metals. So we can just write this here. Here it is only for metals or conductors. So the induction is for metals or conductors only. And how we can charge by induction by getting two spheres, and those spheres, if the two spheres are having one of them is a charge, the other one is neutral. So basically the other one is inducing the charge object is inducing the charge in the neutral object, and then it will be indirectly induced or charged. We can draw this here. If you have two spheres, like a sphere here and another one, this one for example, it is positively charged. Or let's say we have two spheres that they are neutral and connected. Both of them are neutral. And then you have a rod here that is negatively charged. So we can expect that the negative charges here are going to attract the positive charge in the two spheres, so it will look like that. So all of the positive charge will be coming closer in the first sphere, and all of the negative charge will travel to the other side. And finally, we can connect an earth wire here to get rid of these negative charges, or you can simply touch it because your body is going to take the excess of negative charge, and then finally you'll find out that the two spheres became positively charged without direct contact with the charged object. It is the same case here in the figure. As you can see that this is a negatively charged object, and when it became closer to the sphere, it induced the positive or attracted the positive charge and repelled the negative charge. When you connected this to the earth or you touched it, so the electrons traveled through your hand and you ended with a positively charged object. So this is an induction process. An induction process takes place only in metals. Finally, we have polarization, which is also an indirect way of charge without any direct contact. Without any direct contact, but it takes place only for or with the insulators. So this process is only for insulators. So for instance, if you have a comb, and this comb has negatively charged or it is negatively charged, and you have pieces of papers, the paper pieces are neutral while the comb is negatively charged. When it becomes closer to the paper, it will encourage the negatively charged or the positive charge in the comb, and then there will be an attraction. But there will be no complete separation because this is an insulator. That's why we call it polarization. So polarization is an indirect way of a charge. It is rearrangement. Both of them are rearrangement of a charge, but one of them is taking place in the conductors and the other one is taking place in the insulators. So both of them are rearrangement of a charge. And you have to clarify your answer that with no direct contact. This is very important. Okay, then we will go to the electric forces. Electric forces, as we said, in the properties of a charge, that like charge repel and unlike charge attract, and repulsion and attraction is due to an electric force, F. So the electric charge basically is a type of force, and here we are comparing the electric force to the gravitational force, the Fg, to the F electric. So this is Fg and this is F electric. Gravitational force is very small compared to the electrostatic forces. And we have proven this once we calculated the gravitational force between two electrons, or an electron and a proton, and we calculated the electric force between an electron and a proton. We found that the electric force is huge compared, or very large compared to the gravitational force. So the electric force is bigger. The other thing is electric force could be attractive or repulsive, while the gravitational force is only attractive. This is not scientifically accurate, because gravitational force is not considered to be an attractive force. It's a bend in time and place, but for the time being we are going to take it as, or consider it as, an attractive force. But put in your mind that it is not scientifically accurate due to Einstein's relativity theory. The gravitational force is calculated by this famous formula, which is derived by Isaac Newton. It is G m1 m2 over r squared. G is a gravitational constant, which is equal to 6.67 times 10 to the power of negative 11. The two masses divided by r squared, which is the distance between, the average distance between the two objects. Here we used a similar shape, but different formula, different physical quantities. So the force is equal to Kc Q1 Q2 over r squared, and don't forget the absolute value. So the force cannot be negative, it is always positive, but you need to clarify your answer whether your force is an attractive force or a repulsive force. How can I figure this out? They are attractive if they are different, they are repulsive if they are the same. And the unit of the electric force is Newton. There is something very important here. Mathematically, we can figure out that the force is directly proportional to Q1 and Q2, and the force is inversely proportional with r squared. And this is very important and a common question, which is, you need to be able to relate the force to the charge and the distance numerically. So let's say that if Q1 is doubled, so what happens to the F? If one of the Q's is doubled, so F will also be doubled. If the Q is tripled, so the F will be tripled. If both Q's are tripled, for example, this means this would be 9 times. Okay, so this is the relationship. It's a direct relationship. What if we need to relate the F with the R? So let's say that the distance is doubled, which means it became 2. This means that the force is inversely proportional with 2 squared. So the force is going to be decreased with the 4th value. What if it is tripled? The distance is tripled. So this means that the F is going to be decreased by a factor of 1 over 3 squared, which is 1 over 9. We can ask another question, the same question but in a different way. Let's say that if the distance is 2 meters and the electric force is F, what happens if it became 8 meters? So you need to compare the 2 with the 8. So 8 divided by 2, this means that we increased it 4 times. Which means that the R became 4 times, which means your F is going to be less than 1 with a factor of 1 over 4 squared, which is 1 over 16. So these are the kind of questions that you might have if we are relating the force to the factors, the Q and the R. So let's go to the definitions. Coulombs law. Coulombs law, which is Kc Q1 Q2 over R square. It is not enough to write the formula. You need to write the formula and you need to interpret the formula in words. And it is quite easy. Basically, it is easy. Here, where is that? Yes, F. Translating the law in words is quite easy because it is Kc Q1 Q2 over R squared. I can say that the force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So you are just translating the law in words. You are just saying this. The force is directly proportional, the electric force between two charges is directly proportional to, or varies directly with the product, because this is multiplied, so the product of the charges, and inversely proportional with, or to the distance, the square distance between the charges. So this is Coulomb's law, which states that the force between 2 point charge varies or directly or directly proportional with or to the product of the charges, because they are multiplied, and inversely proportional with the square of the distance. Don't forget the square, 1 over R squared. So what is the electric force? Electric force, it could be repulsive or attractive. So it is the attraction or repulsion between two particles or between two charges. Again, which is directly proportional to the charge, the product of the charge, and inversely proportional to the square distance between them. Then we need to go to the electric field. So we are done with the force. Now we need to define the electric field, and the electric field basically is the space, the properties of a space around any charge, and the electric field is defined as the electric force per unit charge. Electric force per unit charge. If you found that this is this definition cannot be memorized easily, you just can recall how you can calculate the E. The E basically is equal to F over Q, F over Q, which means it's the force per unit charge, force per unit charge. And this is the definition, you're just translating the law. So the electric field strength is the force, the electric force per unit charge. That's why it is measured in newtons per coulombs. Actually, we have another way to calculate the E, and as you can, if you do remember that F is equal to Kc Q1 Q2 over R squared, and divided by Q, because this is F, so divide by Q, so 1 over Q. You will remove one of the Q's and you will end up with E is equal to Kc Q over R squared, an absolute value here. This is another way to calculate the E. But this one will be beneficial for the definition, and sometimes we use this formula in solving problems. So you can calculate the E using two formulas: E equals F over Q, or E equals Kc Q over R squared. We need not to forget that Kc is equal to 9 times 10 to the power of 9 newtons meter square per coulomb square. Then the test charge. The meaning of a test charge, we always use the term test charge. And the test charge is the charge on the object that is used to test the field. It is called, that's why we call it test charge. And it should be small enough that it doesn't affect the other charge. That's why we need to use a unit test charge in order not to affect the other charge. This is the main reason of using a unit charge. Electric field lines. Electric field lines are not the force lines, so please do not be confused between both terms. Electric field lines is the direction or the lines that are used to represent the actual field in the space around the charge. And we know that the positive charge are outward direction, while the negative charge is an inward direction. There is something very important that you need to know about the field lines. First of all, that the direction or the positive comes out, while the negative charge line are inward. Here, the field lines always leave positive charge and enter negative charge, and they never cross out. So this is a property. This is very important. This is 1 and this is 2. Electric field lines, they have specific directions. It depends on the charge, and they never cross each other. If you have two charges, positive and let's say positive as well, and both of them are equal, Q1 and Q2, so both of them are having an outward direction, and when the common ones here should be bent like that because they will repel. And as you can see, Q2 has 1, 2, 3, 4, 5. Q1 has 1, 2, 3, 4, 5 because they are equal charges. If one of them is double the other, or it is twice times, or it is triple times, so you need to change the number of lines according to the relationship itself. If you have positive and negative and both of them are equal, Q1 is equal to Q2, so this one is going to be inward here, also here if you want, and you can also put another one, no problem. And as you can see, if you cover this part, you will find that the negative charge has 1, 2, 3, while the positive charge has also 3. Both of them are equal charges. Now let's go to the meaning of the electric potential energy. And electric potential energy is similar to, it looks like the gravitational potential energy, because both of them are energies and both of them are stored, but both of them has this stored energy due to the position towards something else. So if you have an object and this object has a certain height, the gravitational potential energy here is due to this height. That's why it's equal to Fd or mgh. While the potential energy here is due to the position in an electric field. So we will call it work, which is equal to F times R, and you can make your substitution with the F and you will find out. We will discuss the formulas later. So we can say that it is equal to EQR. This is the formula that we are always using. E is the electric field strength, Q is the charge, and R is the distance. And it is measured in joules because this is the unit of the work. So the electric potential energy is an energy. It's a potential energy associated with the test charge due to what? Due to its position, and it is measured in joules. So this is the electric potential energy. I'm stressing on this because most of us sometimes we become confused between the potential energy and the potential difference, but both of them are totally different. Electric potential energy is a potential energy that is associated with the test charge due to its position. But electric potential energy is work done. It is something that should be done. It is not already there. It is something that should be exerted. But the electric potential energy, you are describing the potential energy. Like if you looked at a stone on a mountain and you said, well, wow, this stone has huge it has a huge potential energy. Due to its position, you didn't do anything. But if you pushed it, this means that you are doing something else. So this is the meaning of the potential difference. So the electric potential difference is work done in order to move the positive charge between 2 points in an electric field divided by the field itself, or the uniform field itself. That's why it is the V is equal to E times R. So this is the how we can calculate the V. So this is the electric potential difference, and this is the electric potential energy. Electric potential energy is equal to EQR, while the V is equal to ER. And the electric potential difference is measured in volts. Sometimes we call it V or delta V. So now you can differentiate between the electric potential energy, which is just a description of the charge in an electric field, like the stone. You're just describing the stone, and here you are just moving the stone in an electric. You're in a mountain. Here you are moving the electric charge. It could be away from the electric field, or it could be opposite, or in the same direction of the electric field. And each one has a specific sign that we will discuss later. Basically, in order to move an electric charge, you need a potential difference. Like the stone here, you have very high potential energy, or let's say work, and here you have a very low work, and the stone will move. The same for the charge. If you have huge delta V, huge electric potential difference. So this one would be having work, and this one would be having work. Let's say that this is having, let's say that this is having huge work, and this is a very small work. The difference is a delta V. So if there is a delta V potential difference between the 2 points, the charge is going to move easily from a point to another one. And in this part, the 2 points are having different potential energies. But what if 2 points that they have the same charge, the same W, the same amount of potential energy? So are we going to be able to move the electric charge here between the 2 points? Think about that. Can we move 2 points that they have, a point between 2 points that they have the same potential energy? So the answer is no, we can't, because both of them are having equal potential. So when you have many points, or 2 points that they have equal potential, we call this equipotential. So we have equipotential, and equipotential means 2 points or points that they have the same potential energy. Which means, what is the delta V between those 2 points? 0. So the equipotential has same potential energy, but 0 potential difference. So again, if you have 2 points that they have the same, these points are having the same potential energy, which means that they have 0 potential difference. So this is the meaning of the equipotential. Equipotential means points that they have the same potential energy but zero potential difference, because the potential energy is the same between the 2 points. So if you got the delta or the difference, you'll find that it is zero potential difference. And this is what happens inside the battery. When the battery is new, it has huge delta V. But after some time, delta V would be zero, because the 2 points will be having the same potential energy. So that when the potential energy is equal, the potential difference is zero. So I hope that the meaning of the equipotential is now clear. So equipotential, and it's from the name itself. Equipotential means equal potential, and I mean by equal potential energy, same potential energy, but zero potential difference. So don't miss this point. Here there are some important points. The electric potential increases in the direction opposite to the electric field. So when you are moving opposite to the electric field direction, the electric potential increases. The electric potential is higher near positively charged plates, because you are moving the charge towards, you need to move the charge toward a positive charge. So if you are moving positive charge toward positive charge, this needs work, because there is a repulsive forces. So you need to do more work. So the electric potential energy is high or higher near to positively charged plates. The dimensional analysis of the E, we mentioned that E is equal to F over Q, which means that the unit is Newton per Coulomb. Here, E is equal to F over Q, which means Newton per Coulombs. For the voltage, we mentioned that the delta V, or the V, is equal to E times R, and this came from it is the W over Q, and when you derive the W, which is equal to EQR divided by Q, you remove the Q, so you will find out it is equal to ER, or W over Q, which is the potential energy divided by Q. So the delta V is equal to volt, I mean the unit, or it could be also joules per, good, coulombs, wonderful. So joules per coulomb or volt, but we are using volts. So look at this figure, and the figure here will show you that the positive charge is, when I move the positive charge towards this big positive charge, I need huge work, which means that it's a positive electric potential energy, positive electric potential difference here. So it's not negative, it is positive, because I need work. I need work to move it against the electric force, which is repulsive. Now we move to the capacitance. So we covered now the meaning of electric force, we covered now the meaning of electric field strength, we covered now the meaning of delta V, and we mentioned that this is Kc Q1 Q2 over R square, absolute value, and we mentioned that this is equal to F over Q, or Kc Q over R square. And finally, we mentioned that this is equal to W over Q or E times R. So these are the values that we have taken till this moment. I will summarize them by the end of the presentation. F is measured in newtons, E is measured in Newton per Coulomb, V is measured in volts or joules per Coulomb. Now we go to the capacitance, and the capacitance is equal to Q over delta V, which measured in farad, or there is another unit which is C coulombs per volt. So you can use this or that, but basically we use the farad. And it is, again, if you wanted to define the C, don't lose your time. Just write the formula Q over delta V and say the formula in words. It is the ratio between the electric charge to the electric potential difference. So the capacitance is the ratio between the charge stored to the electric potential difference, which is measured in farad or coulombs per volt. And these are some of the laws. Here this is Coulomb's law, Kc Q1 Q2 over R square. We don't use D, we use R square, so change this. And here we use E equals F over Q or Kc Q over R square. And this is measured in newtons, this is measured in newtons per coulombs. Here it is equal to W over Q or E times R, and it is measured in volts. This is also the law of the electric potential difference. And the C is equal to Q over delta V, which is measured in farad or measured in coulombs per volt. If you looked at this formula basically is one of the most famous formulas in the electricity, which is Ohm's law. Ohm's law is relating three values, V, I, R, and he says that the V is equal to I times R. V is measured in volt, R is the resistance, and I is the current. And this is measured in volts, this is measured in ohms, and this is measured in amperes. You can use this triangle to relate the three quantities. So if you need the V, it is I times R. If you need the I, it is V over R. If you need the R, it is V over I. And this is a very useful diagram that shows you the meaning of each part. And as you can see, the voltage is the potential difference needed to push the charge, which is the current. This is basically the ampere, which is the Q over delta T. And the ohm basically is the resistance. So this is the resistance, and this is the voltage or the potential difference, and this is the current. The more the V, the more the current, and the more the R, the more the V needed to push the amperes or to push the electric current. This is a very useful diagram, but we're not using all of the included formulas, because in the electricity part we used the I, V is equal to I times R, and we used the power, which is equal to I times V. Sometimes I give you the I and I give you the power, and I will ask you to find the resistance. So basically you will use both laws. You will find the voltage, and then after the voltage you will find the V over I to get the resistance, you'll use this law. So a lot of times we use the combination of the power law and the voltage law. The power is measured in watt. So these are all of the formulas that you have taken. So if you wanted to summarize all of the formulas, I think that this would be beneficial. So let's start with the force. Electric force, which is F is equal to Kc Q1 to R square, measured in newtons. Electric field strength, which is E equals F over Q, or Kc Q over R square, which is measured in newtons per coulombs. And then electric potential energy, which is W is equal to F times R, or EQR, which is measured in joules. Electric potential difference, sometimes we call it voltage, which is delta V, which is measured in W over Q, because you need to know how many joules per coulomb needed to move the charge in an electric field, which is E times R, and measured in volts. And finally, you have V, the Ohm's law. Let's remove this. We have the capacitance, which is C is equal to Q over delta V, and it is measured in farad, or coulombs per volt. And you have Ohm's law, which is V is equal to I times R, and finally the power, which is P is equal to I times V, which is measured in watt. These are all of the formulas that you need to know. And let's do something here. I hope it works. So let's draw a line here. Okay, and here, 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 and here. So these are all of the formulas that you need, and these are the units. So these are the units. Here the R is measured in ohm, the I is measured in amperes, the V is measured in volt. And maybe there is one formula that we just missed, which is how to calculate the I, which is Q over T, because the I, or the current, is the rate by which an electric charge or electric charges move from a point to another, which is measured in ampere, which is A, or coulombs per second. So all of these, these are all the formulas that you will need, inshallah. For the resistance basically is the opposition force that the current might experience while passing in a conductor. And as you can see, ohms, or the resistance here, is this opposition force, or the resistance force that tries to to resist the amperes, or to resist the passing of the Q in a conductor. And this resistance can be big amount or can be small amount, and we can basically control it. And the factors of the resistance are 4 important factors. First of all, the length of the conductor. So if the conductor is long, it has a specific resistance, and if it's short, it has another specific resistance. So the resistance for the long wires, the electrons need more distance to move, which means more voltage, so the resistance is big. While if it's a short current, short wire, the resistance is more lower or smaller. So the longer the conductor, the greater the resistance. So the length, when it's higher or longer, the resistance is longer. Cross-sectional area, which is the width of the conductor. And if you have more cross-sectional area, I believe that the amount of a charge will be more, which means that the resistance is low, is so low. So here is big resistance, while here is small resistance. So it is an inversely proportional relationship. So the more the A, the less the R. Then the type of the materials. Some materials are good conductors, some others are not. Then you have insulators, for example, that they don't allow the charge to move freely. General measure of the resistance of the substance, which is resistivity. Some materials are having high resistivity, some others are having low resistivity. So aluminum, for example, is one of the best conductors that we use, while iron is not good like aluminum. Copper. The copper is one of the best. The copper is one of the best conductors, while iron is not good as a conductor, is not good like the copper. But it is, again, it is still a conductor. But for wood, it is not a conductor by any means, so it has a huge amount of resistivity. Finally, the fourth factor is the temperature. So we have 4 factors. The third one is temperature. So the more the amount of temperature, the more the movement of charge, the particles of the conductors, which means that the charges are going to fight their way to pass through these particles. So the resistance would be more. So the more the temperature, the more the resistance, because molecular motion would be more in the higher temperatures. This is a simple electric circuit, and the electric circuit consists of conductors. And you have load, and this is a switch, and as you can see, the switch is open, which means there is no current. And this is a power supply, which gives us the V, or the voltage, which is a battery. Sometimes we can add parallel lines like that, equal parallel lines, and this is a capacitor. So these are the components of the electric circuits. In order to connect circuits, you have this is an electric circuit. This is a battery. This is the main source of energy. This is a switch, or the switch can be like that as well, like here. Rheostat, we didn't take rheostat, so ignore this. Ammeter is the device that measures the current, and voltmeter is the one that measures the voltage. This is a resistor. This is a bulb or a load. We can call it a load. And these are conductors, or we can call it wires. Ammeter is measuring the current, and voltmeter measures the voltage. Sometimes we combine both in one device. We call it a multimeter. It measures both I and V, but you need to change the reading indicator. Finally, the connections. We have two types of circuits, and those circuits are parallel or series. The parallel circuits, the series circuits are just resistors that are connected in one branch or on one path, while and this one path can also be here. So if we have a resistance here, so those are also connected in a series way. While here, these are parallel resistance because the current is going to be divided into two paths. So this is a crossroad, which means this is a branched circuit. So we can draw it in another way. This is a parallel connection, and this is a series connection. Series and parallel. For the series resistors, each resistor has the same current but different voltage. And as you can see, the current is passing through one main road, as if it's a car that moves in one single path. So the current is the same, but the voltage is divided between them. And as you can see, the voltage here is given to both, which means each one is taking a part of this voltage. If the two resistors are equal, so the voltage is going to be divided into two halves. If one of them is bigger than the other, so the bigger one will take more voltage than the other. Here, for the parallel circuits, it's the opposite. The case is totally opposite. So we have a different current, while they have the same voltage. And as you can see, the current it's a car that moves here, and then there is a crossroad. So this car should take one of the roads. Basically, for the current, it gives part of it here and part of it there. So what is divided here is the current. So the current is different, while the voltage is the same. And as you can see, this is a circuit by itself. And if you ignored this is a circuit by itself. So each one is taking the same voltage. Look here at this figure. If you cancel this is a circuit by itself. If you cancel this is a circuit by itself. If you cancel those, this is a circuit by itself. And this explains why each one of the parallel resistors are having the same. This is V, this is V, this is V, and this is V. But the I is going to be I1, I2, and I3. And the total of the three I's will be the same as this. We call it I equivalent. But here the I is going here, so it is the same I, Oh, okay. So it is the same I. Okay, and the same I. But the V is divided, so this is V1 and V2 and V3. In order to do these calculations, you need to use the formula for each one. For a series circuit, you just can add the resistors R1 plus R2, and you can get the total resistance or the equivalent resistance. For the parallel circuit, you will use another formula. I don't like the formula which is written here, but I will give you an easier formula for R equivalent. R equivalent for the parallel circuit is equal to 1 over R1 plus 1 over R2 reciprocal. This is how you can get the total R of a parallel circuit. So, for example, if you have here, if you have 1, 2, 3 voltage and 2 ohms, 3 ohms, 5 ohms, and this is voltage, which is 12 volt. So I need to get R equivalent. R equivalent will be, this is series circuit. So I need to add 2 plus 3 plus 5, which is 7, okay. And this is 2, and this is 3, okay, there is no more. Okay, so they are 10 ohms. And this is what we call R equivalent. So I can change the circuit into this. A battery of 12 volt and one single resistor of 10 ohms. If I have a series circuit, this is a series circuit. If I have a parallel circuit, so 1, 2, 3, and this is also 2, 3, and 5, and this is 12 volts. R equivalent for this parallel circuit would be 1 over 2 plus 1 over 3 plus 1 over 5 reciprocal, which would give you a value in ohms, and you can put this value in one resistance here. This is R equivalent, this is R equivalent, and that's it. So by now we revised most of the theoretical component of this course. Again, we'll go to check our objectives, define each physical quantity calculated, compare the units, and again, a trick for doing this is to define the value from the law itself. Just say the law, write it and say it in words. Compare the units and derive them. We have made a list of all of the values that you need here. So these are all of the laws that you need with the units required. And we here we stated and explained the properties of charge and the meaning of conservation or the quantized charge. We compared between insulators and conductors. Insulators are the materials that they don't allow the charge to move easily or through, while conductors are materials that allow the electric charge to move through. Compare between different methods of separating charge: conduction, induction, polarization. We recognize the direction of the electric field lines, if they are the same, if they are opposite. And we mentioned that they don't never cross out, and the direction also is out from the positive into the negative. We recognize the direction of electric field force between charges and the structure of the electric circuit. We compared the series and parallel circuit, and we calculated R equivalent for both, and we defined the role of voltmeter and ammeter in a circuit. I believe that these are the main points that you will need. Please contact me or post a comment or a question if you have any. Thank you very much for your time. I hope that this presentation is beneficial for you. Please share it with your peers. If you liked the presentation, press like. If you didn't, press dislike. And please share your comments in order to improve these presentation in the future, inshallah. A copy of this note will be posted under this video, so you can go to the website and download this note for your reference. Thank you very much. This is Shady Elkassas, physics teacher and head of science department, Sharjah American International School. Have a great day.